The integration by parts formula that we derived in the previous video is written at the top of this page. So when we're trying to evaluate an integral that has a product in it, as we see here, if we can identify one term in the product to be our u and the other term in our product to be our v prime, then we can just write this formula down and we know that that will be a correct relationship. We not only want this to be true, but we also want this new integral that we have on the right-hand side to be easier than the original integral. And so we have two things to accomplish in our choice of u and v prime. One is that u and v prime should multiply together to be the original integrand. And secondly, this thing over here, vu prime, ought to be an easier integral to do. If those two things happen, then integration by parts will be helpful. In order to decide which part of a product should be u and which should be v prime, we use a heuristic, sort of just a rule of thumb that has the acronym LIATE, and this is our priority list for what should be u in integration by parts. The L stands for log functions, the I stands for inverse trig, the A stands for algebraic, T stands for trig, and E stands for exponential. Now you can easily come up with examples that make this priority list, or that trick this priority list, but 90% of the problems this list will work perfectly. The rationale for the list is that when we apply integration by parts, like I said, we're really just trading in an integral for another integral. And so the priority list for u here is basically in the order of how much I like the derivative more than I like the function. This integral has a u in it, and this integral has a u prime in it. And so this list is in the order in which I like u prime more than u. The all-time winner in that regard is the logarithmic function, ln x. Lots of people in our class don't like problems that have ln x in them. They find them confusing and the property is hard to remember. But the derivative of ln x is just 1 over x, which is one of the easiest algebraic functions to manipulate. So there's a huge difference between working with ln x and working with its derivative 1 over x. Not much different than that are the inverse trig functions. Their derivative of inverse trig functions are algebraic. They're not they're not nearly as nice algebraically as 1 over x, like the log function. But the derivative of inverse trig functions are not inverse trig functions. They're all algebraic functions. So in a lot of ways, the derivative of the inverse trig function is simpler than the original function. At the other end of the hierarchy, when we get down to the other functions, there's not that much difference between the original and the derivative. An algebraic function's derivative is just another algebraic function, sometimes slightly simpler, sometimes not. The derivative of a trig function is just another trig function, and not really any simpler at all. And the big loser in this sort of way of thinking about it are the exponential functions, because not only are they not a different kind of function, that they're often themselves. The derivative of e to the x is e to the x. So there's no difference at all between u and u prime if you were to let u equals e to the x in a problem. So, so that's the rationale for this hierarchy, and that's why it works most of the time. And we will use it in all the problems that you see on this page so that we can practice using our rule. The first problems are just about identifying what should be u and what should be v in each of these situations, and this requires some practice. And I encourage you to practice these because it can be a little hard to get used to the idea of working with u and v prime and u prime and v. It's very easy to get confused about where you are in that process. So here's how we do it. We have an integral of a product. So there's two things multiplied together. Number one, we have x and we have e to the 3x. So one of those will be u and one of those will be v prime in order to match the integration by parts formula. So the priority list says the u should be the algebraic part, the x. This is an algebraic piece x times an exponential piece e to the 3x. So the algebraic should be u, and the exponential part should be e to the 3x. So I have these little tables, or little blanks over here on the left, and I encourage you to use these because it will keep everything straight. So on the first row, I'm writing down the two things that go into my original integral. So the original integral was x times e to the 3x. So that's this first row. Now from there, I need to figure out what u prime and v are. So this is where I have to be careful because I have u here and I want u prime. So I want the derivative of x. Now by contrast, here I have v prime and I want v. That's an antiderivative question. So if you tell me that v prime is e to the 3x, then I know that v is 1/3 of e to the 3x. So I have to use my basic antiderivatives in order to be able to do that. That's actually another place where in this process that it can fall apart is not only do I need to be able to, do I want u times v prime to be simpler, but it's possible that v is actually impossible for me to find, right? I can give myself an antiderivative problem that I can't actually do. So there's another caveat to this whole process that we have to be ready for. But applying, this all worked out. And so applying the rule, now I can just copy it down. So the integration by parts rule says that I should have u times v, and just pay attention to these things. This is u, this is v. So u times v, I'm going to write it, well, I'll just write it like that. So x times 1/3 e to the 3x. So that's u times v minus the integral of v times u prime. The v times u prime is this second row. So v times u prime. And so that would be the setup for integration by parts. That would be a true statement. Remember, it's equivalent to the product rule, so it's not hard to check to make sure that really is what it should be. And so that would actually give me a pathway to completing the problem as long as I believe this new integral is something I know how to do. And in this case, it is. I'm just asking for another antiderivative of e to the 3x here. So I'd be able to finish that problem. Now, I'm not going to finish that here. There's exercises for you to try in a second. I really want in this video to set up all of these. So if you want to try this yourself, pause the video and try setting up the next couple of them, and then I will fill in the gaps. In this problem, I have an algebraic problem, an algebraic part, x squared, times a logarithmic part. My LIATE hierarchy says I should let u equal the logarithmic part. So u should be ln of x, and v prime should be x squared. So my first check is the row of these numbers that I wrote down, these expressions I wrote down, this row is exactly what I'm integrating. Now I need to take the derivative of log of x to get u prime. So this is u and I want u prime. Now this is v prime and I want v, so that's an antiderivative that I need to do. So the antiderivative of x squared is 1/3 x cubed. So integration by parts says this should be u times v, so log of x times 1/3 x cubed minus the integral of v times u prime, so that's 1/3 x cubed times 1/x. I will write one more line down here. I'll write this in this order just so it's easier to look at. I do want to say here, don't forget your algebra. This integrand, if I wanted to continue, x cubed and 1/x, those cancel. So one of these x's cancels with that x. And so I'll have 1/3 the integral x cubed over x is x squared. So it is a much easier integral that I have. This is my integration by parts statement. And the new integral that I have here is very simple. All right, so I just have to figure out what that is, and I have my answer to the original. All right, in number 3, I have an algebraic part times a trig part. And so my LIAT hierarchy says my u should be the x squared part, the algebraic part. And that means that v prime will be the other part, cosine of x. So again, quick check. The product of these two things should be my original integram. Now I have u and I need u prime. So the derivative of x squared is 2x. And over here I have v prime and I need v. And sine and cosine are the hardest ones to keep straight because they just go back and forth between each other. But just pause when you're going to do one of these and think about it. We know the derivative of cosine is negative sine, but that's not what I'm trying to do. I know v prime is cosine and I want v. So that's an antiderivative step. The antiderivative of cosine is sine, positive sine. So the derivative of sine is cosine. So now my new integral will be, we'll have this product across here. So I'll have this integral is u times v, so x squared sine of x, minus the integral of u prime times v, so this row. So that's my integration by parts step. This case, that is not something that we can just do in our head like this one was. And even this one up here, these two could be finished pretty quickly. This one has something interesting going on because it still has a product of an algebra piece and a trig piece. And so I would actually need to do integration by parts again to figure out what this is. So it's like substitution in the sense that applying this rule only trades in one integral for another. If you apply the rule correctly, it trades in an integral for an easier integral, but that doesn't necessarily mean that that new integral is one that you'll just know off the top of your head. You may actually have to apply other steps to be able to figure it out. But I'm sure this one is easier than the one I started with. The one I started with had an x squared in it times a trig function. This one only has an x times a trig function. So it's not a lot simpler, but it is a little bit simpler. And so I feel like if I continue, I'd be able to get that answer. The fourth one is a little tricky because the integrand does not look like a product. And this is, there are only a few extreme cases like this, and they usually involve either the log functions or the inverse trig functions because those are so high up on that LIATE hierarchy. In this case, we want u to be the inverse trig function so much that we're willing to make u equal to the inverse tangent function and have v prime just be 1. There's nothing wrong with that. It's certainly true that the product of these two things is the integrand here. The derivative of the inverse tangent function is 1 over 1 plus x squared. And the antiderivative, or an antiderivative of 1, is x. And so absolutely nothing is wrong with that as an application of integration by parts. I'd have u times v, x times inverse tan x, minus the integral of u prime v, so that's x over 1 plus x squared. Again, that new integral is definitely not something I know off the top of my head, but if that were the only question I had to answer, it should look fairly familiar. We saw ones just like that, and it would require substitution. This problem would work really well with a u equal 1 plus x squared substitution. So again, this one, we didn't get an integral we just knew, but we did get an integral here that was simpler than the original integral, something that we knew how to deal with. The evaluation here, what I'm asking you to do here is just finish these first two problems and get a final answer, and then pop open your Wolfram Cloud version of Mathematica and see if it agrees with your answers. A really good idea, if you want to check things by hand to get more practice, is actually try using the product rule on your answer. So remember, we can check an integration answer by taking our final answer, whatever it is, and take the derivative of it and see if we end up with that. That's very good practice because every time you do that, you'll have to use a product rule and you'll actually see why the integration by parts rule is working. I'll do one of those in a subsequent video. This one's getting a little bit long, but that's what I want you to do there. Those are the same two problems. The last thing I wanted to say in this video is we can use this to find definite integrals as well. And when you do that, just like with substitution, there's two different ways to do it. You can either let integration by parts run its course until you have the complete antiderivative of your original integram and then plug numbers back into it, or you can just sort of evaluate it as you go. and I will do the latter. I will always evaluate as I go, because in these problems where you might have multiple steps, multiple substitutions, multiple integration by parts, it actually is much easier to evaluate as you go. So in this case, the answer to this problem is, I'm having a hard time with my controls, is the integral of the function. This is the log function, so I want the integral under the log curve from 1 to 4. So that's what that region, the area of that region, would be this integral. This is another one like number 4 above, where it doesn't look like a product, but we so much want the u equals log x. We like that so much, we're willing to have u equals log x and v prime equals 1 for this integral, and that the product of those two things is the original integrand. In that case, u prime is 1 over x and v equals x. So integration by parts says that this integrand should be u times v minus the integral of vu prime, that second row. So notice in this case, that's 1 over x times x, and those x's are going to cancel out. Now what about the 1 and the 4? Well, in the evaluate as you go mindset, we would evaluate that first part from 1 to 4 because the integral sign has come off of it already. And then this new integral, we would keep our integration, the limits of integration on that one. So this first evaluation will be 4 log 4 minus 1 log 1. So that's the evaluation of x log x from 1 to 4. Then minus the integral, this is the integral of 1. 1 over x times x is just 1. So that's the integral of 1, which is x, evaluated from 1 to 4. So I have the 4 log 4 for my original thing. Notice that log of 1 is 0, so I can leave that off. I'll just put a line through it to remind you that I'm just not ignoring it, but that is 0. And then over here, with this evaluation, I'll have my antiderivative x evaluated between 1 and 4. So that'll be 4 minus 1. And notice my parentheses there so that my subtraction doesn't give me the wrong thing. And so I'll have 4 log of 4 minus 3 as my final answer. So that's the area of the shaded region for this picture.